Hello YouTube. Today we will be going over the notions of invertibility and isomorphisms. So let's get to it. Here's some motivation for the concept of invertibility. So take a foot and put a sock on it. Well, now you got a foot with a sock. So formally expressed as a function, the notion of putting a sock on, well, you give me your foot and I give you the foot with the sock on it. So P does that putting of the sock. Now, the inverse of putting on a sock is, well, taking off a sock, expressed as a function like this. So you give me your foot with a sock on it, and I just give you back the original foot. And now observe that the following two relations hold. If we do function composition of my p and p minus 1 like this and like this, we don't do anything to our original input. So these two compositions are equal to the identity function. So if you give me a foot and I put a sock on it and then I just take the sock right away off of it, well, I did nothing to the foot. Same here for if you give me a foot with a sock on it, if I take off the sock and put the sock back on, well, I did nothing. So that's the motivation for this definition over here. We say that T, some linear transformation, is invertible if and only if there exists this linear transformation from W to V, which I will denote like T minus 1, such that, well, these two hold. So the function composition is equal to the appropriate identity functions. And now we have a theorem that says the notion of invertibility is equivalent to T being a bijection, so it's the same thing. So let's show that this holds. So let T be a bijection. So we're going from this and we're going to show that T is invertible. Well, due to T being a bijection, it is surjective, meaning that for each W in our big W, we have some vector in V such that V gets mapped to W. And now T is also injective, meaning that to each W in the range of T, there exists only one V that gets mapped to the appropriate W. So due to it, T being injective, we can't have that some V1 and V2 get mapped to the same output. Now, since this is the case, we know that to each V, there's only each V gets mapped to exactly one W, and all of the W's have some originals to them, so like some V's that get mapped to them, so we can just go, well, backwards. We can define the mapping T minus 1 from W to V such that, well, if you give me some W, I will give you the V, where the V is just the thingy that gets mapped to the original W. So we can do this due to T being a bijection. And now all that's left to show is that T minus 1 is linear. So we have to figure out what this is equal to. So to each of these, W's, there are these corresponding V's and V's, such that T of V prime gets mapped to this, and T of V secundum gets mapped to this. And now I'm going to write this using this, so I know that my W's are equal to these thingies. So we have this expression, and now due to T being linear, we get that this is equal to this. Now, this thingy in the bracket over here is equal to this. When I apply T minus 1 to it, the T and the T minus 1 will cancel out. We just do nothing to the output. So we get that this over here is equal to this. And now we can just replace the V's with the T minus 1. So V is just the original of the appropriate W, which is expressed like this. So we have that T minus 1 of this input over here is equal to this, showing that T minus 1 is invertible, is linear. Sorry. Now let's assume that T is invertible, and let's show that it's a bijection. So let's show that it's injective first, take some V's and set them like this. So the images are set them to be equal. And now due to T being invertible, well, there exists this T minus 1 such that this composition over here is just the identity function. So when I apply T minus 1 to this equality over here to both sides, well, I just get, so we get this and this composition is just the identity function, so we just get that this v is equal to this v, showing that t is injective. And now let's show that it's surjective. So since t minus 1 maps from w to v, we have that for each w in w, there exists a v such that t of v is equal to w. And t maps all of v to w. So we have that each w is an image output of some v in v. Thus the whole of v is the image of t, meaning that the range of t is equal to w, showing that, well, t is surjective. So that would be that. And now we move on to the notion of isomorphisms. Well, so observe the following two structures. So I have this thingy over here. So we got some elements, some objects, x, z, and y, and maybe they have some relations among them. And we have over here another structure with some elements a, b, c. So a is not equal to x. They're different thingies. But, so these two are not identical. But if we loosen our notion of equality, identity, equivalence, for example, by choosing to ignore the labels of the elements, so let's imagine that we don't care about the labels in this case, then it seems perfectly reasonable to consider, well, once we ignore the labels, we get these two structures, and they look pretty much the same. So in this case, it might be perfectly reasonable to consider as equal in this context these two structures. So that's the motivation for the notion of an isomorphism. Formally, if I have some vector spaces, we say that v is isomorphic to w, denoted like this, if and only if there exists some linear transformation from v to w that is invertible. So we can, in this example, for example, here we have x, y, and z. Here we have a, b, c. So, for example, if we had the mapping that takes x to a and a back to x and y to b and b to y and so on, well, then we would have shown an example of an isomorphism, and we can move around between these two structures. So, for example, if we wanted to analyze this structure, but it turned out that this structure is difficult to analyze, well, we could just kind of translate and analyze this structure over here, which might be easier to analyze. And all the, well, in this context, all the linear algebra results that we derive for this structure, we can just translate back to this structure over here. Hence why isomorphisms are powerful tools. So we can move around between these two structures. And now we have the following result, which says that two vector spaces are isomorphic if and only if they have the same dimensions. So a line and a plane cannot be isomorphic. They have fundamentally different structures. So let's show that this holds. Let's assume that v is isomorphic to w. Well, then we know by definition there exists sub-bijection, so t is invertible, which also means t is a bijection. So we can use the rank nullity theorem then. So we have that, recall that the dimension of v is equal to this over here. And now, due to t being a bijection, t is injective, meaning that the dimension of the null space of t is equal to 0, and t is surjective, meaning that the range of t is equal to w, and from this we conclude, well, that the dimension of the range of t is equal to the dimension of w. Combining all of these, we get that the dimension of v is equal to the dimension of w. And now we have, so going in the opposite direction, let's assume that they have the same dimensions, meaning they have the same number of like basis vectors. Whatever two bases we pick, they have the same number of vectors in them. So we can just define some t. So if I give you a v, you can write out v as the linear combination of the basis vectors, and I'm just going to map each of these basis vectors to the appropriate basis vector in W to get my vector, to get my output. So that's how we define T. And we can do this due to them having the same number of basis vectors. So for each W, which can be expressed like this, we have that T of the basis vector Vi is equal to the basis vector Wi. So W is equal, when we express these like this, we get that W is equal to this linear combination. And we can just define now our T minus 1 of W. Well, if W is this, and each of these Wi's is equal to this, well, let's just go backwards. So if I have some Wi, just give me back to the Vi that mapped to it in the first place. And once we define everything like this, well, we get that the following two hold. So T minus 1 is our inverse of T. So we assume that they have the same dimensions, and we've given an example of a linear mapping that is invertible. Thus, we can conclude that V and W are isomorphic. Now we have that the dimension of the vector space, so of all matrices of dimension m times n, well, is just equal to m times n. So if we look at the standard basis of, so fix some m and fix some n, and if you look at the basis vectors, the standard basis vectors of that space is just m times n matrices, where we put the one in the corresponding place and we can get all the matrices. Thus there are m times n elements in the basis. So the dimension of this space is equal to this. And now let's show that the space of all linear transformations from V to W is isomorphic to the space of all matrices of dimension m times n, where n is the dimension of V and m is the dimension of W. So to each linear transformation, we can get its corresponding matrix relative to some bases we fix. So we have this mapping M. So M of T is the matrix of T. And we store the appropriate coordinates of the column vectors like this in our matrix. So now let's just define M minus 1 to take in matrices and to give me linear transformations in the following way. So if I give you some matrix S, you will give me the linear transformation some T of S, such that T of S, when I give you a vector V, it will act upon it in this manner. So x1 to xn are the coordinates of V, and these are it's the action of T of S on the basis vectors of V. Now, how do we get these TS V1 all the way to TS Vn? Well, we just I gave you a matrix, take the columns of S to get the appropriate TS of Vj, like this. So I'll give you a matrix, and you will take this column, the jth column, and this will be the action of T of S on the basis vector. This will be the image of that. So since we know all the basis vectors of W, and we get the coordinates, these over here, these scalars from our matrix, we can just figure out what this is. And that way we have defined M minus 1 to give us meaningful linear transformations. And the following hold. So if I give you a linear transformation and I take its matrix and then I just go back from the matrix back to T. So in M of T, we have all the appropriate column vectors with the coordinates corresponding to the images of the basis vectors, and I just go backwards and derive T again. So it's the identity. And same here. So if I give you some matrix, I get some T from it with the appropriate images of the basis vectors, and then M will just take those coordinates and put them back into a matrix, and that will be equal to S. So these two hold. Thus, our space of linear transformations from V to W is isomorphic to the space of matrices of these dimensions. And now we can derive the following. It turns out that the dimension of the space of linear transformations is equal to the dimension of V times the dimension of W. So, since these two spaces are isomorphic, they have the same dimensions. That means the dimensions of this space is equal to this, and we know that the dimension of this space is equal to m times n, where n is the dimension of V and m is the dimension of W. Hence, we have that the dimension of this space of our linear transformations is equal to the dimension of V times the dimension of W. So, using isomorphisms, we managed to calculate the dimension of this space, which we were not able to do before. But we managed to, using isomorphisms, we can, since the dimensionality of a space gets preserved, so they have if two spaces are isomorphic, they have the same dimensions. In this space, it was hard to figure out what the dimension was, but in this space, it's very easy to conclude what the dimension is. So, since we've established the isomorphism, we've been able to conclude something new about the space. And now we introduce the following notion. So let T be a linear mapping from V to W. We say that T is a linear operator on V if and only if the W over here is equal to just V. So T maps from V to V, which we will denote like this. So here we have a major result for linear operators. So let T be a linear operator, then the following holds. All of these three statements are equivalent. So if T is a bijection, well then obviously T is injective and T is surjective. But for example, if T is injective, then it also follows right away that T is surjective, meaning that T is a bijection. So just from having one of these, we get a stronger property bijection. So usually we just have that if some mapping is bijective, well then it follows that it's injective and it's surjective. But for example, if T is injective, it doesn't have to follow that T is a bijection. It doesn't have to be surjective. So usually this is the case. But here, for linear operators, we have the following. So if T is bijective, well then, by definition, it's injective and surjective. Okay, but now if T is injective, that means that the dimension of the null space of T is equal to 0. And now, using the rank nullity theorem, we get the dimension of V is equal to the dimension of range of T. And we get, well, T maps from V to V, and the dimension of range of T is the same as the dimension of V, meaning that the range of T has to be V, showing that T is surjective. So we assumed it's injective, we got it surjective, hence it's a bijection. 3, if we assume that T is just surjective, that means that the range of T is equal to V. Well, that means that the dimension of range of T is equal to the dimension of V, and from the rank nullity theorem, we conclude when these two cancel out in the expression, we get that the dimension of the null space has to be equal to 0, meaning that T is injective, hence T is bijective. So for linear operators, in, again, finite dimensional vector spaces, we get the following. We get all of these equivalences. So just from knowing that T is injective, we can safely conclude that T is a bijection. So that's a very powerful result that holds for linear operators on finite dimensional vector spaces. And yeah, that would be all in today's video. Hope you learned something. Have a good one.